Hi everyone. Today we will discuss our tutorial number 10. Today's discussion will be continuing from where we left in the previous tutorial. that is the discussion on equilibrium constants. Okay, so we will further explain or discuss about how to calculate, like how the equilibrium constant is related with the partition function, different types of partition function of a chemical reaction. Okay, so before doing that, let me discuss the things that we have uh, learned in the previous tutorial. Okay, so recap, just give you a brief recap. So we started our in last tutorial. We started from the contribution of different partition function in the specific heat of a particular molecule. Okay, so suppose, so we have discussed that. So there are in the specific heat at constant volume. Let's denote it by CV. Has different contribution, right? So one contribution comes from the translational, one contribution comes from rotational, one contribution comes from the uh, vibrational, okay, and one contribution comes from the electronic. Okay, so in our previous discussion, we have shown through some examples that how basically, if you know the partition functions from different contribution, so from that, how basically you can calculate the specific heat at constant volume. So first case that we have discussed is in the case of a rotational contribution to the partition function. Okay, so because translational part you already know, right? The translational is 3 3 by 2r in case of 3D, right? In case of 3D, and 1 by 2r in case of 2D. That we already knew from our previous discussion, also from the kinetic theory of gases. You already know this is the contribution that comes from the translational part. But if you move forward from the translational part, the rotational part comes in. So so in order to calculate the rotational contribution, what we did, well, the first and foremost thing that we have to check is the temperature. What is the temperature of the system? Okay, our interest. Okay, so if the temperature is higher than the theta r, the characteristics rotational temperature, then only we knew that the significant contribution from the rotational partition function will be added into the system, right? So if that is the case, if T is greater than theta r, we know the uh, we know that in that case the rotational partition function QR basically takes the form 1 by sigma in C beta B, right? So where sigma is the factor which takes 1 for case of heteronuclear nuclear molecule and 2 for homo homonuclear molecule. Okay, 1 and 2. Okay, right. So QR basically, so this is the expression of QR. Now if you knew QR, from there you can calculate the internal energy, right? Because in order to calculate the specific heat at constant volume, you need the expression of internal energy. So first the internal energy is ER, sorry, it's basically U minus U0 per mole per atom is basically the ER. The average energy is this basically. The internal energy, total internal energy of the system divided by the total number of molecules gives you the average energy. And the expression of U minus U0, we know that that is 1 by N, so minus 1 by Q rotational del Q rotational by del beta, right? At constant volume. This is the expression of average energy, average rotational energy. Okay. Now from here, if we want to calculate the CV, the specific volume, so CV F rotational is basically uh, that means Na for a mole. Na means mole, so that is del Er by del T constant volume. That basically gives us K into Na or R, right? So that is we have done. That is the case for t greater than theta. If t is not greater than theta, then the ER expression will take a kind of a complex 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 equation like this, something 6c to the power 2 beta hcb like this. Then in the denominator there are terms like this, c to the power minus 2 beta hcb. So this takes a very cumbersome expression, energy expression. Now if you derivative, now this is the case where t is comparable to theta, right? Now for this case, the CVMR or expression will also be again become very much complicated, because you have to take the derivative of this whole rotational energy term, right? Average rotational energy term. So this is the case actually. So you have to just put this here, you have to take the derivative, right? Now this is the case for the rotational term, right? Now so for in general case, when the temperature is higher than the theta, CVMR is okay, the rotational. That is the case of linear rotor. Okay. Now if you consider non-linear rotor, okay, then the expression will change. Then the expression will simply become 3 by 2. That is for the case of non-linear rotor. Okay. So linear rotor and non-linear rotor. Okay. So this for this derivation we have considered. For this derivation we have considered the linear rotor case. Now if you consider the non-linear rotor case, the CVMR expression will simply takes 3 by 2r. Okay. Now next contribution comes from the vibrational term, right? So the vibrational energy is defined as EV, the average vibrational energy. Expression is EV angular bracket hc nu tilde by e to the power beta hc nu tilde minus 1. Now here the nu tilde is basically the frequency of the activated vibrational modes, right? So nu tilde is the sorry, not the frequency, it's a wave number, right? Wave number. So we knew that like there are multiple independent modes of vibration are associated with the vibrational partition function, right? So each of these vibrational modes actually independently as an independent contribution to the total vibrational partition function, right? So anyway, so if you take the similar way, if you take the specific heat with respect to the vibrational modes, then it will take the similar form, like so Na into delta EV by delta T, which basically gives you this sort of a form where theta V by T whole square by e to the power minus theta V by 2 T by 1 minus e to the power minus theta V by T whole square into R. Okay, so this is the expression of CVMR. Okay, now theta V is just like the case of rotational, theta V is the characteristic vibrational temperature, right? Now if you take theta V, T, our experimental temperature is much higher than the theta V characteristics rotational temperature, then this CVMR or the vibrational contribution simply takes the value 1. Okay, that is for when the T is much higher than theta V, right? So So that means there are basically three contributions. Electronic contribution we are not considering because it has a very negligible effect on the specific heat. As in order to activate those electronic modes, you actually needs a very high temperature. Otherwise, there is like no need to take its contribution. Okay, so so now let me write all the contributions in a compact way. So CV is, we can write at n mole as half 3 into 3 plus mu r star plus 2 mu v star plus r, right? So this 3 by 2 r, this comes from the uh, translational this contribution comes from the rotation, and this contribution comes from the vibration. Okay, here nu r star is uh, 2 for the case of linear rotor and 3 for the case of non-linear rotor, and nu v is equal to uh, 1 if all the modes are activated. So okay, all the vibrational modes are activated, then nu v takes the value 1. Okay, nu v star. So these are the different contribution from different partition functions that attribute to the total specific heat at constant volume. Now we have discussed some problems regarding this. So in those problems, basically a molecule is basically given at a specific temperature, and all its like vibrational frequencies, vibrational modes are mentioned. So in these kinds of problem, what we did first, we have first checked whether it's a linear. So for translational partition function, it's fixed. It's in 3D case, it's 3 by 2 r, right? For rotational part, what we did, we checked whether the temperature is first we check whether the molecule is linear or non-linear, right? So depending upon that, this value of nu r star will be decided. So for non-linear case, we took it equal to 1. For non-linear case, we took it equal to 3. And next, we have checked whether the temperature is high enough to the characteristics vibrational temperature. We compare, we first calculate the characteristics vibrational temperature for each independent modes of vibration. And we have checked whether the temperature of the experiment is higher, much higher than that characteristics temperature, in order to know whether all the vibrational modes are activated or not. So if that is the case, where all vibrational modes are activated, we took the nu v star value equal to 1. Okay, and next next we have discussed about the residual entropy. Okay, so residual entropy is basically the temp. We know that the temp. So let me write it. So let's see. So from the law of thermodynamics, we know the entropy of the system. The minimum value the entropy of the system can gain is equal to 0. The entropy cannot become negative, right? So the residual entropy of a system is basically the entropy at T equal to 0 Kelvin. Okay, this is basically known as the residual entropy. Okay, so this basically comes because of the configurational disorder of a system that we have discussed. So let's suppose two molecules A and B, which are basically identical to each other. So let's suppose in a lattice structure, whether the lattice is oriented like this, A B AB, AB, or it can be like this, AB or BA, and again AB. So as both A and B are similar kind of a molecule, so whether it's making a bond AB or it's making a bond BA, it doesn't actually affect the total energy of the system. Okay, so basically making AB to BA doesn't comes as a cost of energy. Okay, so it can basically it can take uh, this configuration and this configuration with equal probability. Okay. So because of that fact, the total configuration of the system at T equal to 0. So this whole thing is happening at T equal to 0, right? If you increase the temperature because of the thermal motion, so there would be disorder in it comes to the system, that is for sure. But at T equal to 0, there is no thermal fluctuation there. So this is a kind of a inherited disorder that exists into the system, that is known as the configurational disorder. So whether it's taking the bond AB, it's favoring the bond AB, or it can also favoring the bond BA, that is totally random. Okay, so so if this is the case, then the total configuration of this kind of a structures is W equal to 2 to the power n, if total number of molecules is n. So it can take AB or it can take BA. So two types of combination are possible. So the configuration is 2 to the power n. So the entropy, in this case we know, the entropy you can easily calculate from the configuration, that is K into ln W. So this is K into ln 2 to the power n, so nk ln 2. Okay, so this is basically the residual entropy of the system, of that particular system. Also, if you make the system highly polarized, okay, so like A has a high electronegativity compared to B, it's negative and it's positive. So if it's like this, so in that case the bond would be like this, right? A A B, so A B at equal to 0, right? It's minus plus minus plus minus plus. Now because of this recent introduction of higher electronegativity and lower electronegativity, and this concept of polarization, right? So because of that, if you make the configuration instead of AB, if you make the configuration BA, that means the plus will have to come closer to this plus molecule, and the negative will have to come closer to this negative molecules, right? Which basically make the total energy of the system is higher. So this opposite configuration basically comes at a cost of the energy, which is basically is not permissible, right? So in this kind of system, this configurational entropy that I've discussed in our previous system, where AB molecules is exactly similar, is not true in this kind of a polarized kind of a molecule, right? Where it has a higher electronegativity compared to B, right? So the electronegativity is not, so configurational uh, disorder is not possible. So for that case, the total configuration W is simply equal to 1, right? So this is the only configuration that is happen, that is permissible. So 1 to the power n, that basically gives you 1 itself. So the entropy would become Sk ln 1. Ln 1 is 0. So the entropy is 0. So for this kind of system, there is basically no residual entropy exist. Next, what we've discussed is about the equilibrium constants. So we know that in a chemical reaction, knowing the equilibrium constants, like when basically the chemical reactions comes at an equilibrium, well, we can calculate the equilibrium constants, right? From their reaction concentration and from their stoichiometric coefficients, we can calculate the equilibrium constants. which is a very important quantity to calculate in order to basically control the rate of the reaction. It's a very important quantity to calculate, right? So in our previous discussion, we just briefly started about how this equilibrium constant is related with the partition function. Since in this course we are whole thing is about this partition function. So we want to further discuss how this equilibrium constant is directly related to the partition function. Okay, so if let's suppose this is a reaction C into C plus T into T. For this kind of a reaction, so if this reaction is in equilibrium, okay. Now from this reaction, the simpler expression that we have already that we know from our lower studies, that K equal to the equilibrium constant, K equal to C into C, D into D, D to the power D, E to the power A, and E to the power B. Right. These are basically this things in the square brackets denotes concentration, right? And A, B, C, D are the small A, B, C, Ds are the stoichiometric coefficients, right? So this is the very much rudimentary way of calculating the equilibrium constants, right? And so also in this kind of a reaction, the other important thing is the Gibbs free energy, right? Because whether the reaction is spontaneous or not, it depends upon the Gibbs free energy, whether its value is negative or zero or positive at constant temperature and pressure. That basically decides whether the reaction is spontaneous or not. So the change in the Gibbs free energy, or the delta G, is written like this: delta G is equal to delta G0, that is the change in Gibbs free energy at in the standard conditions, delta G0 plus RT ln Q. Q is the total partition function. So this results is already established from the previous classical thermodynamics, right? And this is the change in G in standard condition against TU. Okay, and from our previous discussion, we know the change in Gibbs free energy standard condition is minus RT by ln K. From the statistical point of view, from our earlier discussion, we have derived this relation also, right? So that means we can write okay, so so this is we have discussed from our previous studies, right? Now we can write now from here the change in Gibbs free energy, uh, G minus G0 equal to MRT ln Q by N. This is the case where we want to basically convert the total partition function into the molecular partition function. So We know for case of discrete molecules, distinguishable molecules, you can write a total partition function like this form. So the Gibbs free change in Gibbs free energy will take the form like this, and you can also divided the whole thing by n. So this gives you the molar change in Gibbs free energy G0m at 0 equal to minus RT by ln Q by n. This you also can write. Now for a chemical composition J, chemical composition J, we can write the Gibbs free energy Gm0J minus Gm uh, J comma 0, this is at absolute 0, minus RT ln Q J by N, right? Now let's take a reaction like this. So for the case, let's take a reaction like this. A plus BB after reacting with CC into DD. So GMJ is, you can write GM0J comma 0 minus RT ln QJ by NN. Right. Now delta GMJ is simply A into GMJ plus P into GMJ. You can write it like maybe A GMB minus C into GMC minus D into GMD. Okay, you can write it like this, or we can write it in terms of summation like this: J into mu J GM J comma GMJ. This, now if you also write the left hand side, the right hand side of the equation like this, so that would be, gives you summation over J mu J GM J comma 0 minus summation over mu J RT ln QJ minus N by N. Okay, that is the total change of the Gibbs free energy during the reaction, right? Now so delta GMJ is so we can further, so nu J we can write as this whole thing is written in terms of summation, so this is multiplied with the ln, so we can take this nu J into the power of this ln, right? So you can rewrite this thing J J comma 0 minus R summation over J RT ln QJ by NA into mu J. Okay, this is the specific form of the change in the Gibbs free energy. You can further simplify it. Simply, what you can do is, we know Gibbs free energy G is basically U plus PV minus TS. Okay. So that means PV we already know is equal to nRT. So U plus nRT minus TS. Okay. But if the temperature is, since the system is in equilibrium, so change in temperature delta T is simply 0. So change in the Gibbs free energy delta G is only depends on the delta U, right, at 0. At G at 0, delta T is 0. So we can write the change in Gibbs free energy at T equal to 0 in terms of change in the internal energy at temperature 0, right? So that means you can write it like this: delta Gm equal to delta U0 or delta E0, whatever way, change in internal energy, total energy, equal to J into RT. We can take, since it's ln, so the addition of ln we can write as a multiplication, right? So RT ln of sum, the multiplication of J U J by N to the power mu J. Okay, so this is the change in the Gibbs free energy of that particular species J. Okay, so this is how the Gibbs free energy. Now the next thing is, so this is, we just calculated how the Gibbs free energy change at standard condition, definitely. So this is whole thing is actually happening at standard condition G0. So this is all G0. Okay, so everything is basically happening at standard case. Okay, now this is the change in Gibbs free energy standard case that you have derived from this equation, right? From this equation, right? This equation. Okay, this whole thing is derived from this equation. Now we also have another equation, right, where the change in Gibbs free energy is related to the equilibrium constant K, right, that we have derived from a statistical point of view. A couple of lectures maybe earlier we have derived this. So what we will do next discussion is that we will basically compare these two. Okay, so we have this and you also have this Gm0 equal to minus RT log K. Okay, so let's name this equation 1, this is equation 1, this is equation 2. So if you compare the equation 1 and 2, from there we will get a mathematical relation between the equilibrium constant K with the partition function Q. That is the thing that we basically want to derive, right? So you got this. So what you have to do, you have just to compare these two things. So comparing 1 and 2, what we got is minus RT ln K equal to delta E0 minus RT ln sigma G into QG N0 NA into mu G equal to ln K equal to minus delta E0 by RT plus ln sigma G equal to QG N0 by NA into mu J, right? Now if you take the okay, so now what you can do, you can write this whole thing, just this we are doing just to make this whole relation less complicated, right? So we can write this thing in terms of exponential, right? So we want to actually cut out the ln thing on the both the sides, so that's the reason we are doing this. So ln e to the power minus delta E by KRT. So this is the same thing you will get in the previous step. So now into ln sigma J QG N0 by NA into mu J. Okay. Now from here, so what you can do, you can write ln k equal to ln of summation over j q j m0 into na to the power mu j into e to the power minus delta e by rt. Okay. So from here, the expression of the k would be summation of sigma multiplication over j q j n 0 by n whole thing to the power mu j into e to the power minus delta e by rt. Okay. So this is the relation that we desire to find out, or we got this basically. So how the basically the equilibrium constant is related with the partition functions of different kinds. So this is the whole thing, the whole expression, right? We basically now we will use this expression to find out different kinds of. First, we will start from some simple problems where we'll discuss like in equilibrium. From the reactions, we actually calculate the by calculating the partition function of both the reactants and the products. Uh, we will calculate the equilibrium constant. So first, let's take a easier example where disassociation is happening. So X2 is a molecule. After the disassociation, this X2 molecule gives 2 X atoms. Okay. So now for this case, what would be the expression of this constant, equilibrium constant K? So here the first thing, the nu j is nu1, let's say nu1 is 1 here for the case of X2. Stoichiometric coefficient is 1. For the second case, the stoichiometric coefficient nu2 is 2, right? So that means K is Q. Sorry, it's nu g is minus 2, right? No. It's here. It's minus 1. Here it's plus 2. Yeah, now it's fine. Plus 2 and minus 1. So Q first. So QXM0 by NA into plus 2 into QX2M0 by NA minus 1. So these are the two some multiplicative terms into to the power delta E minus by RT, right? So delta is basically the disassociation energy that we are talking about. Okay. So now, so here from here, what you can say that this, since this is a to the power minus 1 term is there. So basically 1 Na will cut from each of from the sides. So this basically gives us Qx n0, this thing will whole square, 2x2 n0. This is just no power in here into delta E by RT. Okay, this is the equilibrium constant. Okay. Now, so this is a specific form we got for the equilibrium constant for this kind of expression where X2 is disassociated into 2x atoms. Okay. Now the next thing is, first let's start from the delta E. So what is possibly delta E would be for this reaction? So delta is simply the energy that is required to disassociate the molecules. So basically to rip apart those two atoms inside the molecules. So for that ripping purpose, we need this disassociation energy. So delta E is basically the disassociation energy that experimentally can also can be measured, right? So this you can write as d naught. Okay, disassociation energy d naught. Next is the partition function. Okay, so now we have to calculate the partition function. So first is the for qxm. So qxm is in the numerator. So qxm. Okay. So for qx, x is just a normal molecule, just a single atom, not a molecule. It's just a single atom, monoatom. It doesn't. It's a just. It doesn't have any rotation. It doesn't have any vibration. It doesn't have any electronic contribution. So the only term, only contributions comes from uh, the translational part, right? The translational qtx. Okay, this is the for case of x. Now for the case of x2, multiple contribution comes because it's a diatomic molecule. So that means it has a rotational contribution, also can have a vibrational contribution. So it has qtx2, qrx2, qvx2. For this discussion, let's not consider the electronic contribution, right? So let's take up the vibrational contribution. So these are the contribution that is possible for x2 since it's a diatomic molecule. That is the region we have. So we have these three different types of contribution, partition function contribution, right? So now what you can write, you can simply write the k as uh, so let's take the qxm first, right? So the translational part is simply Vm by lambda x whole cube, right? This is the translational because that this only has a translational contribution. It doesn't have any rotational contribution. Um, so we can write the qx equal to Vm by lambda x. Now for the x2, this has also the lambda x2 cube into qr x2 into qv x2, right? So after getting all of this, uh, substitute all of this thing here. So k is this expression, so k is this. So here in terms of qxm and qx2m, we just substitute these two. So let's do it. So k equal to now become uh, so lambda x2, sorry, so qx, so first is the qxm, right? So this would become Vm by lambda x cube, the whole thing will be squared divided by Vm by lambda x2 cube into grx2 into q, sorry, qrx2 qbx2, that is into e to the power minus d0 by rt. Now you can because both this both these molecules x, whether it's x and x2, basically are in the same volume. Okay, so we can cut the volume terms, right? So volume terms we can cut from here. After cutting the volume terms, we'll be getting with, so lambda x2 will become above this cube into, along with the Vm. Vm is also there in numerator, so in denominator it will be lambda 6 to the power 6x into rotational x2 and vibrational x2. Both are there into e to the power minus t0 by rt. So this is the equilibrium constant k. Okay. So one more thing that you can do actually, since this whole discussion is about when the system is in standard state, right? So we can basically write this Vm, P0 Vm0 equal to RT RT0 nRT T0 basically. So anyway, um, since takes n equal to 1 for 1 mole, so we can write Vm0 in terms of RT by P0, since the pressure is 1 bar, right? That we know in standard case. So that means we can write this whole thing Vm, this take Vm0, since it's standard condition. So this thing here will be 0. Okay. So you can write the K as, so instead of Vm0 you can write Kt by P0 into lambda cube x2 by lambda to the power 6x qr x2 qv x2 into e to the power minus t0 by rt. So this is the sort of a form of equilibrium constant that we're getting here. Okay. Uh, yeah, it's fine. So this is the form of the equilibrium constant K for this kind of a equation where disassociation is happening. So now this is a very much kind of a very much small, very basic problem that we discussed. Now let's take a bit complicated case where the reaction, typical form of the reaction we will take, which is looks like the C into A plus C into A plus B into B is in equilibrium with C into C. Now for this kind of equation, the K is K, the expression of K remains the same. Let me write it first. Is the multiplication over J Q J in 0 to the power Q J 0 in pi in A mu J into e to the power minus delta, since it's T0 by RT, right? So for this kind of reaction, so summation over J, so nu J, we know the stoichiometric coefficient, so we can write it like this: Q J M0 to the power Na by Na to the power minus A, because the stoichiometric coefficients are generally minus A, minus B and C, right? Small c. These are the stoichiometric coefficients. So you can write it like this into Q Jm0 by Na to minus B by Q Jm0 by Na to the power C into to the power minus D0 by RT. This is the simply the form of the stoichiometry, so you can write it much more compactly like this: Qjm by 0 by Na to the power C divided by Qjm 0 by Na A into Qjm to the power by Na into B to the power minus D0 by RT. This is the expression of the K for this sort of a reaction, a very general type of a reaction. Okay, so D0 is the reaction, the change in energy that happens when the reactants A and B forms the product C. During that process, whatever the change is, that basically comes here as D0. Okay. So if that means that, let me just summarize the things briefly. So so uh, so we started from the Gibbs free energy, change in Gibbs free energy, okay, at standard condition. So that's the basically this form, right? So this forms we got from the classical thermodynamics from here basically. So where the delta G, we are not considering for delta G for right now. We are only considering the standard case. So delta G are making 0. Only take delta G0 equal to this. Okay. So now from here, we have written this Q is the partition functions. So the total partition function, the system partition function in terms of molecular partition function. From there, for there, we calculated for a reaction like this, what is the change in the Gibbs free energy, right? For the reaction like this is basically the change in the Gibbs free energy. But nu J is the stoichiometric terms. Okay, this is the final expression of change in Gibbs free energy. Also, we know the change in Gibbs free energy from our discussion of what is this statistical mechanics. This is the another expression of changes in Gibbs free energy for the standard case. So what we did, we have basically, so this change, the second case is where the Gibbs free energy is related to the equilibrium constant K. Okay. So what we did, we simply compared both these two terms in order to get the value of K in terms of the partition function Q. So we have compared these two terms, and at the end we got this sort of a relation where the K is related with the partition function. There are other terms are there like the stoichiometric coefficient, the change in the energy during the reaction. So to basically see how things are going on. So we first took a very easy example where the X2, a diatomic molecule X2 basically disassociates into two X atoms. For this equation, for this reaction, the stoichiometric coefficients are given nu1 equal to -1, nu2 equal to +2. So what we did, we just substitute this coefficients into this equation of this equilibrium constant, and from there we got this sort of expression of the equilibrium constant. Okay, so delta is the disassociation energy. And next what we have did, we have we have basically written the explicit contributions in the partition function. That means the contributions that coming from the rotation, translation and vibrations. So for the X molecule, the X atoms, to be fair enough, so X atom, it's basically it's an atom, right? So so it's a monoatom, so monoatomic molecule. So this it's a thing like the vibration and rotation exists there, right? So only things that will contribute to the translational term. So this is the translational term. The other two terms is the for the X2 thing, that is on the reactant side. So for the X2 side, since it's a linear molecule, linear diatomic molecule, so there will be the translational part, there is a rotational and a vibration. So we have written the expression of those two terms, and we have substitute those two things here into the expression of the equilibrium constant K. And after doing some simplifications, we got this expression of the equilibrium constant K, which is purely written in terms of the lambda, which basically the thermal wavelength, the Vm. Later we basically we have substitute Vm in terms of the pressure and the constant. Since it's a standard case, so it would be helpful for us if we deal with pressure, because in case of standard, in the standard case the pressure is simply equal to 1 bar. So it basically helpful for us if we deal with pressure rather than the volume. So we have substitute the volume in terms of pressure, and there are this rotational vibrational contribution that comes because of the X2 molecule, and the change in energy is basically the D0, the dissociation energy. So we put all the things together and we got this expression of this equilibrium constant K, right? Next thing is a typical type of a reaction we are taking, chemical reaction. So here A and B are basically reacting as a reactant, and it gives the product as C. So first identify what are the stoichiometric coefficients, and as it's necessary to determine the exponent. So K, the equilibrium constant, is basically the summation, the multiplication of all this partition function to the power the exponent. So we put out all the exponents in top of this partition functions, and we put the change in energy that we are taking, the reaction, like the energy that is created or destroyed during this reaction is the change in energy basically. So that we are taking at D0. So we are putting this thing into this expression, and after that we can write this whole equilibrium constant K like this. Right, so this is a expression. So from here you have to calculate each contribution of this partition function, the rotational vibration of each of the molecule, and after putting all these values here into this expression, we'll get a numerical value of the equilibrium constant. This is how we can calculate K. Next we will took some example. Okay, so let's take an example. Okay, example problem where the chlorine Cl2 is becoming 2Cl. Okay. Now for this, evaluate the Kp, or the equilibrium constant Kp for this reaction at T equal to 1500 Kelvin. Now the rotational constant value B is given 0.083 centimeter inverse. The vibrational wave number Nu Tuesday. Only one vibrational wave number is given, so that means there is only one mode is active there. The dissociation energy T0 is also given as 242 kilojoule per mole. So this is the expression that is that is the value that is given. Okay. Now from this all information we are going to calculate. Also the electronic degeneracies are also given. You can use that if you want. If the temperature is really high, you can use this. So there would be another one contribution. So for right now, let's just ignore that thing. So the main thing is, so Q is simply the K. K, you already know the K form is this. Sigma J. Now from here, Cl2 is becoming crystal. So nu has the part, so the stoichiometric coefficient nu has value +2 and -1, right? So for the Cl2, it's take -1, and for Cl it's take +2, right? So K would be simply Q squared Cl by N squared divided by Q Cl2 by Na equal to the power delta E by RT equal to Q square Cl by Q Cl2. This Na, one Na will be cancelled to the power delta E by RT. This is the equilibrium constant K. Now from here, so what you can do, you can write, so QCl has only one contribution. Since it's just an atom, so it only has a translational partition function contribution. So QCl is basically QTCl, right? Where translational part is there. For Cl2, since it's a non-linear molecule, so QCl2 is basically has translational part, it has vibrational parts, so rotational parts, and the vibrational parts. Okay. So it has all the parts like this. So now from here you can easily write it. So partition function K, you can write it like this. So QT CL whole square to the power QT LA2 into QR CL2, sorry, CL2 QV CL2 and 211 and d to the power minus delta E by R2. Okay. Now from here, QTCL is simply Vm0 by lambda cube Cl, and QTCL2 is same Vm0 by lambda Cl2 cube. Okay. Now if you substitute this here, it will take the form Uh, so VM0 cube would be there. One VM0 cancel with each other. So there would be a term of VM0 by Na into lambda CL2 whole cube by lambda CL2 because 6 into the translational, rotational, vibrational terms are really Ra CL2 vibrational CL2 into e to the power delta E by RT. Okay. So this is the expression of the equilibrium constant K looks like. Now from here, uh, what you can do, you can use this form where uh, you know EV here is P0, VM0 equal to RT. RT you can write as K into NA T P0 VM0. So PM0 by NA, you can write it as KT by P0. So you can write A equal to, this K is different. So this is the equilibrium constant K, this K is the Boltzmann constant. KT by P0 into uh, lambda CL2 whole cube by lambda, sorry, this is CL. Yeah, lambda, sorry, this is, yeah, it should be CL. It should be CL. Lambda CL2 multiplied by lambda CL divided by 6 into 1 by QR CL2 QV CL2 into by delta U by RT. Okay. So K is simply, okay, now the lambda is the thermal wavelength. Lambda is given by beta h by n half into h by 2 pi m at to the power half. Okay, this is the typical expression of thermal wavelength lambda. Okay, now so this expression you can easily calculate, right? So since you know the temperature of the system T is already given in the problem, so both for the case of lambda CL2 and the case of lambda CL, you can calculate, right? Or what you can do, Kt into P0, if you substitute this, so that means the first would be some constant, let's suppose uh, R in, not R, M into M to the power uh, T to the power 3 by 2, right? Here this would be M into T to the power 6/2, right? And for the QRs, QR we know if temperature you have to check. So theta R is basically given by HCB by K. So the rotational constant B is given into the problem here. B is given into the problem. So using B, you have to calculate the value of theta R, and if T is much greater than theta R, so that means we can simply use the expression of QR. This simplified expression of QR, where QR equal to 1 by sigma HC beta B. Now here, since it's a homonuclear case, so sigma will be 2, right? Next is the vibrational. Okay, so for the vibrational also, uh, the QV looks like this: 1 by e to the power 1 minus e to the power beta HC nu tilde. Nu tilde value is already given. So both the expression, this for both this expression is for Cl2. So you have to just calculate the Cl2 for the Cl2 both the expression and just put up here. Now for this case, since Cl2 has two modes, two atoms, so the normal modes of vibration for linear molecules, we know 3n minus 5, so 3 into 2 minus 5, so that is 1. So that's why we have to just use only one QV. So we know QV comes from the number of independent modes. If there are 3 modes of QV1, QV2, QV3 is there, provide the case that T is greater than equal to theta V1, theta V2 and theta V3. That's for that case all the 3 modes will be activated, otherwise the values will be very much close to 1, right? So since it's just one is there, like there's one independent mode is there, so the contribution, there is only single contribution, right? So that means it will be 1 by 2 say C theta B into 1 by 1 minus e to the power minus beta AC mu theta into e to the power minus delta E by R2. This is the expression of constant K. This is the whole expression. So now we can also further simplify it actually. So K is now further simplified again. So now the Tt would be become, so T to the power 3 minus 3 by 2. So 6 minus 3 by 2. So it will T to the power 3 by 2 T. So 3 by 2. So this basically becomes K into P0. The M0 will cancel, so it will become T to the power 5 by 2 actually. It's 3 by 2, it's to the power 2. So T by 2 to the power 3 by 2, so 1 minus 3 by 2. So T to the power half, or T to the power minus half, yeah, now it's fine. T to the power minus half, okay. So T to the power minus half into e to the power delta E by RT, whole thing is divided by 1 by 2hc beta B and 1 by 1 minus e to the power beta hc net beta. This is the expression of the equilibrium constant K. Now from this expression, everything you know the temperature, you know the change in the dissociation energy delta E, beta hc, these are all constants, kb, these are all constant, pressure is also constant. And you also have the nu tilde value, the vibrational frequency, you know the B, the rotational constant. So just by putting all those values into this equation, you will be getting a value of K. the equilibrium constant. Okay, so this is a type of a problem. Next, we'll discuss another type, a bit complex type of. This is a simpler case where just simply a dissociation is happening. Now we will consider a more complex problem, okay, where reaction is happening. So let's take the equation like this, chemical reaction like this. CH3OH plus BCl makes CH3OD plus HCl. Now for this reaction, let the K at T equal to 800 Kelvin. So many informations are given. First is the rotation. Since you can see these are all the nonlinear molecules are there. So for HCl, DCl, these are the linear diatomic rotors, and there are also nonlinear rotors. So CH2OH and CH3OD. So for that case, all their rotational constants are given. So rotational constant. So for HCl, B equal to 10.593. DCl, it's B equal to 5.449 centimeter inverse is centimeter inverse. For CH3OH, the A equal to 4.25, B equal to 0.823, C equal to 1792, CH3OG, the A equal to 4.05. These are all centimeter inverse, right? Centimeter inverse. B equal to 0.780 centimeter inverse. C equal to 0.745 centimeter inverse, centimeter inverse, centimeter inverse, centimeter inverse. Okay. Now these are the rotational constants are given. Okay. Since these are non-linear molecules, CH3OH and CH2OD, so these has three 3D for 3D case. So these are three rotational constants, right? And so we will come into how this whole thing is affecting the partition function. We'll come into it. Let me first write all the information. And lastly, the uh, for the vibrational case. So for the vibrational modes, the frequencies or the wave numbers are given for CH3OH. It's the 3735295028401450 and 1033. For CH3OD, it's 27202950294014501033. For HCl, 2991, DCl, 2154. Now, okay, so since we got all the terms, um, so let's first write the K. Okay, so here the whole the so the first let's write the stoichiometric terms. Okay, so stoichiometric terms are -1, -1, +1, and +1, right? So for the products it's plus, for the reactants it's minus, right? So the K, the constants are is, you know, let me first write the expression, is the old good expression, summation multiplication over JQJ M0 by Na to the power mu j is the stoichiometric coefficients. It's whole thing into e to the power minus delta E by RT. Okay, this is the expression of the constant K. Okay, now the thing is, so now uh, after getting this, the next thing what we'll do is K is equal to so K would be equal to uh, Q0 BCl, sorry, HCl U0 CH3OD by Q0. So as the stoichiometric coefficients are of 0, H2O, sorry, not H2, it's CH3OH into Q0 DCl into to the power delta E by RT. Now for HCl, Q0HCl, there are rotational term, rotational HCl, first translational, rotational, vibrational HCl, right? Similarly, for uh, CH3OD, translational CH3OD, rotational CH3OD, vibrational CH3OD. Similarly, Q0 CH3OH, you can calculate Q translational CH3OH, Q rotational CH3OH, Q vibrational CH3OH, and at the end Q0 DCl is Q translational DCl, Q rotational DCl, and Q vibrational DCl. Okay. So we will do it step by step. Okay, so first we will only take the rotation. Translational term we already know how that thing will be contributing. This lambda, just have to calculate the lambda. So first take the rotational. Okay, so for the rotational part, rotational looks like this, right? So Q rotational HCl into Q rotational CH3OD by Q rotational CH3OH by Q rotational DCl. So now for HCl, there is only single this since it's a diatomic linear rotor, so the expression of this case would be QR would be KT by sigma HCV. Now you have to check here, provided the condition is the temperature is much higher than the theta R. In that case, sigma is equal to 1, since not equal to 1, it's a heteronuclear molecule. So it would be KT by HCB, and B is already mentioned here, right? This B for HCl. Okay, this is the value B for HCl. Okay. Similarly, for CH3OD, sorry, for CH3OD, QR would be this expression, right? So this is a non-linear, right? So this is a non-linear case, so that means 1 by sigma KT by HC to the power 3 by 2 into pi by ABC. Okay, to the power half. ABC, the for CH3OD, the ABCs are given. Similarly for CH3OH, same expression, and for DCl also same expression. Okay. So now what we have to do here basically, so just substitute whole thing here. Substitute all this whole thing into this expression here. So this basically gives you, now if you substitute the whole thing here, so all this KT by HC beta B DCl into 1 by sigma KT by HC 3 by 2 pi by A B C, that is at CH3OD to the power half by KT by HC beta B HCl. Sorry, this this is HCl, this is DCl into 1 by sigma KT by HC 3 by 2 by pi into ABCH3OH to the power half. Now from here, all these KT sigma, these constant terms will be cancel each other, so will be left out with ABC CH3OH. Since for this case also both all the molecules are not equal, right? So Yeah, so for both the cases sigma equal to 1, for this case also sigma equal to 1. See it in the video. Yeah. So CH3OH into DTCl by ADC CH3OD into BHCl. So this, so we just substitute all the values. So that would be the multiplication of uh, 4 into 25 into 0.823 into 0.792 into TCL. It's 5.449 divided by 4.05 into 0.780 into 0.745 into 10.592. So you have to multiply all of this, which is gives you some number, right? This thing is basically the contribution that is coming because of the rotational contribution to the partition function. Yes, yeah, rotation contribution to the partition function. This is the what is you call, this is the contribution to the equilibrium constant flow. Okay, so next thing is the vibrational constant. Okay, so for vibrational we know vibrational constant is dependent QV. It's written by QV. Is basically is a multiplication of all the vibrational modes, right? It's, if there are three modes are there, so three independent modes are there, so QV equal to QV1, QV2 and QV3. These three are the three vibrational modes, right? Now QV is written by 1 minus e to the power beta Hc nu tilde. Okay. For provide the condition temperature is much higher than the theta V. For that case, QV would take this form, right? Now, so now for this case, for we know for nonlinear molecules, the number of modes of vibration is given by 3n minus what's it, 3n minus 3n minus 5 or for nonlinear. For linear, it's 3n minus 6 for charge. Yeah, this is for linear, this is for non-linear. This is for linear, this is for linear. So for linear case, that means for like HCl and DCl, the number of modes of vibration is 1. 3n minus 5. So 3n, so 2 into 3 into 5, so 6 minus 5 equal to 1. And for CH3OH or CH3OD, the modes of vibration would be since there is so 4 molecules are there, so this means this number of modes of vibration will be 6, right? So that's why there are 6 frequencies are given for CH2H and CH2OD, and 1 frequency is given for HCl and DCl. Okay. Yeah. So now, for the vibrational part, uh, QV. There will be QV. The equation looks like this. So QV CH3OD into QV HCl divided by QV DCl into QV CH3OH. Now for Q, this one, there would be 6 contribution: Q1, Q2, Q3, Q6, and for this there would be just one contribution. Here also for QV is one contribution, and for this is 6 contribution. So, for each of the contributions, how can you calculate it? So, let's suppose for ACH3OH or CH3OG, there are 4 frequencies are given, like 6 frequency nu tilde, the wave, sorry, these are wave number, not frequency, 3735, 2950. So all these numbers are given, the wave number. So corresponding to that, for each wave number, you have to calculate the QV, this thing you have to calculate, and you have to substitute it here and multiply all of these things. And before doing that, you have to also check whether all the modes are activated or not. If it is not activated, also you will only get one. That's not a problem. Okay. So whatever it is, so so this is the case. So this is the way you can calculate the vibrational contributions. Okay. Uh, After calculating the rotational and vibrational part, the last thing that we have to calculate is the delta E. Okay. Delta is nothing but the basically the energy. Okay. The energy that you can calculate is from the 0 point vibrational energy. So these are the basically the vibrational energy states, right? So if we know the 0 point vibrational energy, the difference in the 0 point vibrational energy in the case of the reactants and the products, then from there we can basically calculate the delta E. So delta E by Hc is nothing but the summation over J into stoichiometric motion mu J into mu J tilde. This is a stoichiometric quantity, this is the wave number. So from here actually we can calculate the delta E, the change in the energy. So that means we have now all the things. We know the partition function due to vibrational, we know the partition function due to the rotational, and we also know by taking the difference in the 0 point vibrational energy, you also can calculate the change in the total energy due to this reaction is happening here. So after getting all of these, just substitute all of this into this main equation. This equation, and after doing that, we will be getting the equilibrium value constant K. Okay. Now next we are discussing a bit different thing. Okay, so these are the discussion that we have done. It's mostly based on how we can calculate the equilibrium constant basically. Equilibrium constant for different cases, different types of reaction. We started with the easy reaction, and then we take a complicated reaction where you have to calculate say like the contribute like partition function contribution from vibrational and rotational modes, and from there you have calculated how you can basically calculate the equilibrium constant. Now the next thing that we are going to discuss that how you can basically calculate the Gibbs free energy. One way the Gibbs free energy can be calculated is from the equilibrium constant, right? So uh, okay, so let me write. Gibbs. So, one way to calculate the Gibbs free energy is uh, delta G at standard condition is minus RT into ln K. Now, K is here the equilibrium constant K. Okay. Now, so that means in a reaction, if you know the equilibrium constant K, from that itself you can calculate the delta G, the change in the Gibbs free energy. There is another way you can calculate the Gibbs free energy, which is the for which we will be considering the thermodynamic definition of the Gibbs free energy, that is delta G naught equal to delta H naught minus T delta S naught. So delta G naught, that means is dependent on both delta H naught and delta S naught. Okay, so that means that if we know the change in enthalpy and change in the entropy of any kind of a reaction that is happening on, so from that two quantity itself we can basically calculate the change in the Gibbs free energy. So this is basically gives us a different way to calculate the Gibbs free energy, right? So for that, let's take an example. Okay. Let's take a reaction where R and P are in equilibrium. Okay. Now for this kind of a reaction, if we can draw its energy level, first let's draw the energy level for R. Let's suppose R is in a relatively lower energy state. The energy state looks like this. At equilibrium, it basically takes a Boltzmann type of distribution, and for T, it looks like this. So this is for R, this is for T. Okay. This change is still there. Now, here what is basically happening here? So as the reactant is at a lower energy state, so this is all thing is at equilibrium. Okay, at equilibrium. So that's the reason this occupancy takes the Boltzmann distribution kind of a form. Okay, so the thing is for the reactants, as you can see, since the whole energy level a bit low, bit down with respect to the products, so for that reason the number of accessible states is also higher in the case of reactants, right? So as a result, so total number of molecules, uh, total number of molecules are also the number of total molecules is also higher in case of a reactants compared to the products, right? So that means the R is more dominant here. Okay, so let's write this as delta E is positive, so the total population in R is R dominates over P since higher number of accessible states are available. So delta is greater plus positive value. So for that reason, for reactants, the overall population dominates over the products. Okay. Uh, so that means what I want to say that is, um, if you can calculate this delta E or this change in the energy, okay, that basically this change in the change, basically the change in the what is this called? Change in the energy of reactants and products. From there you can basically get the enthalpy. So delta E gives you delta H, that is the change in enthalpy, and the population distribution gives entropy, right? So if you get hold of both of these things, delta E and distribution, which actually directly gives you the measure of change in change in enthalpy and change in entropy, right? So from basically that I want to say, so by just by getting this energy distribution and their relative energy level difference, you can basically calculate the Gibbs energy. Okay. Now in the next case, what I will do, uh, this ratio of the number of atoms, number of particles, total number of particles. Okay, for the case of products and for the case of reactants is related, and the relation is given by Np by Nr equal to Qp by Qr into e to the power minus delta E by Kt. How this relation is coming, that we will basically discuss in the next class. For today's class, just follow through my the discussion. So from here actually, if you know the K, so this is the way you can calculate the K also. Because for K also, if you look at the relation of the K, it's also written like this, right? Nu j, nu j 0, nu j by EA into to the power delta E by RT, Now for this kind of product reactants, you can write it as K equal to Q E by Na divided by Q R by Na into e to the power minus delta E by R, right? Now from here, what you can do, so it will takes the form QP by QR into e to the power minus delta E by R, right? This is the expression of K. So this is the same expression here also, right? So we can, that means we can write K as equal to in P by NR into e to the power minus delta E by RT, right? Sorry, equal to QP by QR into e to the power minus delta E by RT, right? This is one of the way you can write the equilibrium constant K of A. So, so it just give you like the both the ways how you can write. If you know the population, like if you know the population fractions of reactant product molecules, so from there itself also you can calculate the equilibrium constant K. Okay, this is one of the way. Now, how this whole thing is happening, that we'll discuss in the next class. We will start from the next class itself, how this whole thing is basically coming. Okay. Um, so for today's discussion, that's it. So we have done a lot of things. We have started how the equilibrium constant is related to the partition function. We've done some problems regarding that. And at the end, we have discussed how you can basically calculate the Gibbs free energy if you know the energy distribution of reactant and products. And also we have discussed there's a relation between the equilibrium constant K and with the number of particles, products and reactants. Okay, so this is a, so further discussion we will do in the next class. Okay, for today's discussion, that's it. Start the meeting.